So we've got a lot of expressions for how to calculate flow velocities and pressure gradients if the flow is fully developed in either a parallel plate channel or a pipe, but we don't yet know when it will be fully developed. So that's the point of this part of the lecture. So we've got, imagine let's start with just a pipe, got some kind of velocity coming in with an average velocity here, flow coming in. It's got some entrance length, and during that entrance length period, the viscous effects are near the wall, but they gradually increase and penetrate into the pipe. And then at some point, the whole flow is being affected by viscosity, and it goes to a fully developed regime where pressure is working against those viscous wall-driven effects. So we want to know how long is this entrance region. So we know whether when we're analyzing a pipe, we really should treat it as a fully developed pipe, or do we have to take into consideration the fact that maybe it's not fully developed, maybe we're still in the entrance region. We're going to call the entrance length L sub E. That'll be our entrance length. And we're going to entrance length. And the other important thing to recognize is that we're really talking about, at the moment, we're talking about laminar non-turbulent flow. So for what we call laminar non-turbulent flow, laminar is the type of flow we've been studying, but the important thing is it is not turbulent. And we are going to get to discussions of turbulence today, and we'll talk about what turbulence really is and when it occurs. But for the moment, we're saying it's not turbulent. The flow is a specific type of flow. And in that type of flow, we know that delta over x is of order, and I'm going to put in a 5 here, Reynolds number based on x to the minus 1/2. So we know that this number is actually 4.92 if we want to make this kind of approximately equal there. So I'm going to put in a 5 there for the purpose of this analysis. Again, this is going to be a scale type analysis, but I'm going to keep the 5 there. It makes the result come out a little more accurately to what we actually see in the experimental systems. So the flow is fully developed when this delta, which is the flow, the growth of this viscous layer into the flow. Remember, we had that for flow over a plate, delta of x was equal to 4.92 Reynolds number based on x to the minus 1/2. So, this flow coming into the entrance of the pipe, it doesn't know this isn't a flat plate. So it actually behaves fairly much like a flat plate. It doesn't know there's another piece of material above it yet until those two viscous boundary layers meet. So we can approximate, the growth of this delta, and when that growth of the delta gets to the height to the middle, that is d over 2, if you make this pipe have a diameter of d, that's when the two boundary layers will merge. And so that's an approximation for when it will actually become fully developed. So when delta is approximately diameter over 2, flow will be fully developed. That's what we're suggesting as a way to approximate this. So we go ahead and plug, that into here. And so we say, well, okay, d over 2 over x, when is that going to be about equal to 5 Reynolds numbers x to the minus 1/2? And when that happens, the flow is going to be fully developed. And this now is the distance here in the x direction, how far we go in this direction, in the direction of the pipe, before the flow is fully developed. So we'll just solve this for x, and we get actually a really good estimate for when that flow becomes fully developed, along with an understanding of why it's become fully developed. So we're going to move that x over to the other side. So we have d over 2 on the left, and I'm going to move the Reynolds number over to that side. So it's going to come over here with a positive exponent, and that's going to all be of order of 5 times x. Well, we know, of course, that the Reynolds number is made up of u bar, and then x and nu, because it's a Reynolds number based on x. That's why there's an x in there. And then we move this 2 over to the other side, so we've got 10x on that other side. And this is, of course, all raised to the 1/2 power. So I have to pull that x to the 1/2 out to put all the x's on one side. So I'm going to have 10x to the 1/2 on one side of the equation, or the order of magnitude equation. And then on the other side, I'm left with d and I've got u bar over nu. And that's still raised to the 1/2 power. Or if I wanted to turn this into a Reynolds number, I can. I can say this is 10x to the 1/2. That's going to order d to the 1/2, and I'm going to put one of those d's in here. So I'm going to put a d into this thing there. So that's going to give me a Reynolds number based on d. So I'm going to have 10x to the 1/2 is of order d to the 1/2 times a Reynolds number based on d to the 1/2. Okay, so now I'm going to finally solve for x here. So I'm going to divide by, I'm going to move the d over. So I have x over d to the 1/2, and I move the 10 over there. So I have 1/10 times Reynolds number based on d to the 1/2. And finally, I square both sides, and so I get x over d is of order 0.01 Reynolds number based on d. And that is my approximation. I'm going to say that that is my LE. So my entrance length, I think, is going to be of order, over d is of order 0.01 times the Reynolds number based on that d. And that is my approximate answer. And if you look at experiments for this, you get that L over D is approximately equal to 0.06 Reynolds number based on D. So pretty darn good, actually. We're a little off as usual by like a factor of 6 in this case, but we do get a pretty good answer, and that's where the Reynolds number based on d is defined as the average velocity times d times nu, which is nice because the average velocity, of course, is the easier one to calculate, to figure out. So again, the point here is, yes, there's an answer. You can calculate the entrance length. That's your entrance length calculation. You can approximate it using this or calculate it using that. But also to really understand where that's coming from. And it really is coming from the fact that these viscous effects grow into the flow, in the delta boundary layer that we studied over a flat plate. They grow into the flow when those two viscous boundary layers merge from opposite sides or all around the center of the tube and converge in the center of the tube. Then the flow becomes fully developed and the velocity no longer changes in the x direction.